So let us discuss about the efficiency of steady flow devices such as isentropic efficiency of turbines. So this is how you calculate the turbines. This is an expansion process. This is a high temperature, high pressure, and this is low temperature, low pressure device, and the expansion is taking place. And remember, the inefficiency usually the in the numerator you have a smaller amount, and the denominator you have a larger amount. So if you take a look, this is smaller, so that's why we have this is numerator h minus h1 minus h2a, and divided by h1 minus h2s. So this is how you calculate on the Mollier diagram, which is h versus s or s. So now let's do the next slide here. So if I show you the next slide, as I mentioned, in the numerator you have a smaller term for efficiency, isentropic efficiencies of compressor and pumps. So for the compressor, so the work done, isentropic compressor work divided by actual compressor. So actual is this one, h1 minus h2a minus h1, which is larger, isentropic is smaller. So that's why you will write this down. Similarly, for the pumps, you will have v p2 minus p1 over h2a minus h1. Okay, let us solve one problem here. So I can show you this problem. The question is steam at 4 megapascal. So steam at P1, so I will say P1 it is 4 megapascal, and T1, which is 350 Celsius, and exit pressure is 120 kilopascals, and saturated vapor. So if I draw the vapor line and the liquid line, this is liquid line, vapor line on the TS diagram. So we know that the expansion takes place from higher pressure to low pressure. This is high pressure, this is low pressure. Since it is saying the saturated vapor here, so of course the second point is over here. This is the second state point. The first state point is we have to look into the steam table, and it turns out that this is in the superheated vapor. So if this is superheated vapor, so suppose this is lying over here, this is 1, so this is isentropic line, both. This is 2s, I would say 2s, this is 2. So this is the actual expansion, the isentropic expansion, as you can see from this diagram. This, so actual is 1 to 2a, and ideal or reversible 1 to 2s. So in the numerator you have a smaller term, which is h1 minus h2a. So I would say h2a is this one. So you have to find out what is the isentropic efficiency of the turbine if the steam is exhausted as a saturated vapor. So turbine efficiency, I would say h1 minus h2a, h1 minus h2s. So looking at the table h1, so you can find out h1 and s1. So table A4 will help you to find out these h1 at this pressure and this temperature. So and A6, this will help you to find out. So A6 gives you 3093.3 kilojoules per kilogram, and S1 is 6.5843 kilojoules per kilogram Kelvin. So we have found this from the table. Now we are interested in finding out the H2, and for pressure at H2, and looking at the table at 120 kilopascals, so x2 equals to 1, so you get H2 2683. I'm sorry, this is 83, not 38. This is 83.1 kilojoules per kilogram. And now, so in order to find out H2S, so we have to find out P2S, which is also equal to P2, which is 120 kilopascals. And since we know that this is isentropic efficiency, so these are two constant values, and at those constant values, which is this one, which is equal to this one, you get what? You get H2S and X2S. X2S equals to 0.8798 using this formula. So S1 equals to SF plus X2S SFG, and from here you can find out H2S. So after you do this, you can apply this formula. I'm sorry, this is, so let me use this formula to plug in the values here. So after you plug in all these values, you get 0.603 or 60.3%. This is your answer.